So welcome back. So today we will start, actually continue where we stopped last time. Again, the idea of the whole networking protocol stack. This is a very good terminology which you need to know. I mean, one of the takeaways of this course is basically you leaving and say, I know what a network protocol stack is. Again, the name is very intuitive. It's a protocol stack. So these are protocols stacked on top of each other. Again, like I stack books, I stack files, I stack protocols. And this is very interesting because the whole foundation of networking is based on protocol stack. If you've done any networking in your life, or you will end up doing networking, you would understand that I design my network based on a stack. And again, this kind of mimics the whole logic of OOP. What does OOP stand for? Be quick. It mimics the logic of OOP. If you're a computer scientist, you should know what OOP stands for. OOP, come on. Thank you so much. Thank you, Harsh. Bonus point for Harsh. So object-oriented programming, 100%. It mimics it. The logic is so similar. Is I have classes. You could always imagine these layers as classes. You could imagine their interface between each other as functions or methods that they give to each other. So I call a function from one layer to another. That's we said, again, interface-wise. You have protocols as well. These are functions, but typically end-to-end. So you can see the logic is very interesting how networking was designed from the beginning. And the logic is even teaching it. There is kind of different approaches. Some professors, some universities come and say, you know what? I'm going to teach it top down. I'm going to go ahead and say, you know what? I start with the application, you know, because students relate to applications. Say, I know what application I'm using, and go down. That's what we call top-down approach. Okay? And there's the other approach, which is, in my opinion, more important, and basically Tannenbaum, which is the most famous book in computer networking. It's the bottom-up. The bottom-up. Okay? Bottom-up meaning I say, you know what? This is the layers. Let's try to understand how the physical layer works. Once I get that, the physics behind it, I go to the data link and understand, oh, what do I get from the physical layer that I give it to the data link? It does some magic. Then I go to the network layer, it does some magic until I come to the application layer. That's what we call bottom-up, because it really allows you to understand that if I have a cable, I always make the analogy, the cable is the physical layer. Cable or wireless, doesn't matter. This is the physics, the zeros and the ones, the signals, you know, the amplitude, the phase, the frequencies. So all the physics behind it. And when we talked about it last lecture, how wireless communication works, I think you started understanding the physical layer, the basic of the physics, the electromagnetic waves, electrons moving, leading to electromagnetic waves, you know, and this electromagnetic waves attaching an antenna allows me to transmit it, you know, and again, this logic is the physics behind it. Once I understand the physics behind it, and this is, by the way, today, it's all about the physical layer and a bit of next week, then I go and say, you know what? I have all these bits, but it doesn't make sense to send zeros and ones. A lot of people who don't know much, they say, computer science is all about zeros and ones. It's not. Anybody knows? Once I have zeros and ones and signals, what do I do with them? What do I do with them? What do you think I do with them when I come to this layer? What do you think I do with them? The logic. Do you think it makes sense every time? Yeah, of course I do process them, Muhammad, 100%. But basically, what kind of processing? That's my question. Convert them, process them. These are all fine. Yeah, compile them. You're all using different verbs that mean the same thing. But what do I do with them? Think about it. Do you think it makes sense every time I want to send something? I send one bit that goes to America to the Google server. Then I send one bit, it goes to the Google server. Do you think that makes sense? Obviously, it doesn't make sense. So what do you think we do? Oh, guys,
do you make it into packets?
It's too early for some of you. Actually, it's too early for me. I'm a night person. So, but you need to wake up. Wake up. So do you think it makes sense to send zero? Somebody's talking some language. Packets. I mean, somebody said packets. I like it. I like it, Afrazali. Well, again, packets make sense. So what do you mean by packets? Can you clarify? Packets, what do you mean? Okay. Packets contain data. Okay, datagram. Okay, people are just sending just any word they know, just put the chunks of data. I like it, Malak. Chunks of data. That's something makes sense to me. So I like when people are putting some words, you know, synonym, just type. Okay, very good, very good. Okay, I like it, I like it. Afrozali, finally, Afrozali decided to reply to my question 5 minutes ago. Okay, excellent. So yes, I mean, just to make your life easier. So yes, we have zeros and ones and bits here. Obviously, as I go up or down, we bundle them. That's the word I'm looking for. All these fancy words you guys threw on me, we bundled them. We bundled them together. Okay? So what does it mean? Instead of sending 0, 1, 1, 0 alone, 1 alone, 1 alone, we send 0, 1, 1. We call it, again, not always a packet. Actually, it's called the packet when we come here. This is when it becomes a packet. Before that, it's not a packet, it's called a frame. You know? And here it's called a bit. You can see the logic, right? The logic is interesting. Is every single layer basically has a unit. My data has a unit. Here the unit is bit. I'm working with bits. When I go up, I work with frames. When I go up a little bit, I work with packets. And that's what we used to. That's the most common terminology, packets, because we're sending them back and forth. Yes, Sarah, yes, this is not rocket science. Bit, frame, and packet. Do we have to memorize? I mean, this is not even a question. Let me reply to it, okay? So bits become frames, frames become packets. And this is the whole logic behind networking, is I'm working with this data from the very basic terminologies in order to end up getting to the application language. So think about it that every one of these layers have their own language, okay? So I hope this kind of made you understand. Obviously, I could click on slides, but some of you just keep on asking questions. Just what I need you to know is layering is very important. Different concepts were brought up when the whole layering thing came out. The famous one is the OSI. The other famous one is the TCP/IP that ended up becoming the leading protocol stack that we use for the internet. However, for those who don't know, that's not the only one. We use other protocol stacks out there. Again, we could apply it in different networking frameworks. Okay, let's move on. So as you can see here, this kind of applies the logic of how networking works and something I was kind of talking about now. The physical layer on one end, the physical layer on the other end, as you can see, physical layer, and then, as we said, within the subnet, we have these 3 layers. What does it mean within the subnet? It means these are the ones that we are jumping hop by hop. So end to end, we don't work with the whole protocol stack. We only work with, basically we work with all the 7 layers, as you can see. However, hop by hop within the subnet, we work with the 3 layers. And that's very, very important. Again, when we did performance management in one of the chapters before, he said, let me analyze the end-to-end delay. Basically, when you were looking at the subnet, which means we were looking at the 3 layers, the physical, the data link, and the network. So one more time, we have an interface. As you can see, we have protocols. The physical layer from one, suppose I'm sending, as you can see, computer A is sending to computer B. This could be Google, for you to understand. This could be your computer, your mobile phone. This could be your iPhone. It doesn't have to be a computer, of course. And you're kind of Googling something. So what's happening is your message is going from one switch to another. And these are switches, again, typically kilometers away. Of course, within your local area network, you will have something. So within your LAN, you might have a Wi-Fi router. You know, this is within the LAN. These are things, these are gateways and switches. These are bigger. You know, we're talking about kilometers within the country and so on, of course, within the WAN, not within the LAN. We're talking about a wide area network here, okay? So yes, very simple. I Googled something, the logic behind it. As you can see, the physical layer, data link, and network are the things that are allowing me to jump from one switch to another until I get to the physical layer of Google, okay? And then I go all the way up to the application, typically the server. It's gonna query, come up with the answers, and then go down again. And then again backwards. You see, it's very interesting. So you can see the physical layer, data link layer, and network. These are the ones that work within the subnet. And then you have the transport, session, presentation, and application. These are the ones typically working end-to-end, peer-to-peer. Peer-to-peer meaning they kind of go all the way down from one end, all the way up to the other end. In between, we don't go all the way up, or not, we don't go all the way down. We only go all the way to layer 3, and then go all the way down to physical layer, then go all the way up to layer 3, until we come to the last destination. Okay, very interesting. So let's talk about these a little bit one more time. I think we've talked about this before. So you can see the message grows in size because we're adding headers and checksums to it, you know, tails. Every layer does its own magic. Again, they do that. They add these, you know, typically here it's something as well. Why do we do that? Who could remind me? Why do we do this? Why do we add the head and the tail typically? Why do we add stuff to it so that who could understand? It's not always error, Sarah. It's not always error. Error is only in the data link. But why do we do that? Who cares about the header? Who's going to read this? Why do we do that? Not
because
the next layer,
protocols
not
are
the next layer, the receiver. Yeah, what layer? Who could tell me what layer? Come on. We need that for what? We're adding stuff to it for what? For protocols. Yes, Afrazali. Wow, today you're on fire. Bonus point for you. So for the protocol, we're doing this because of the protocol. Because who's going to look at it? Who's going to look at this H6? Who's going to look at it? Not the subnet. No, not the subnet. Not the subnet. No. Who's going to look at H6? Who's going to read it? Who's going to look at it? Not the system. What layer? Yes, what layer? Okay, I think it's easy for me to start answering my own questions because it's going to take a lot of time. Obviously, this guy's going to look at it. Okay, this guy's going to look at it and try to understand. So this is for the protocol. These things are added so that on the receiver end, we can understand what you did with the data, because what the protocol says, do the following, and on the other end, I'm going to go look at this and say what you have done with it and try to utilize it in order to understand the data. So of course, these are being added because the protocol needs information. Again, an example will be error detection, not here. Typically, error will be layer 2. You know, this is where we do the error stuff. For example, every layer has a job. Every layer has something to do. And that job defines what we will be doing with my data. Okay, so these are being added so that the other end, the protocol, will understand what we are doing with the data. So that's the logic behind it. Okay, so yes, on one end we're adding stuff to it, on the other end we're removing stuff while understanding the data. This is the basic logic behind a protocol stack. So let's go over the job of every single layer in simple terms, of course. Why simple? Because in the next weeks we will go in details, including today. We'll be talking about the physical layer. So one more time, the plan moving forward is for me to try to explain for you the job of every single layer. You know, some of them are redundant, some of them don't do much, as you would see later on. However, some of them do a lot of work, as you would see as well. So we'll be talking about the job, that functionality. As I said, every layer has a job to do. So the networking is not as simple. I click, magically the message goes to the other end. No, no, no. It requires us to do a lot of stuff in between. And when I say us, meaning the software and the hardware, they're doing a lot of things with the data in order to understand it on the other end and getting it back. Okay? So what we'll be doing in the coming weeks is basically talking about the responsibility of a single layer, because the course introduces you to computer networking and makes you understand the foundation of each one of these layers. Because if one day you'll be designing your own network, hopefully soon, say, oh, I have a network, how many layers do I need? So when I do an Internet of Things, for example, it's not based on TCP/IP. It's not based on what we use for the internet, because it doesn't make sense. I don't need all these layers. I could use 2 layers, one for the physical, one for the application. I could skip some of these layers. So the OSI, when they designed it in a way for you to understand what we can do with layering. It doesn't mean that it is what we will be end up using. It doesn't mean that what we use is 7 layers. Even TCP/IP is not used in many, many different networking applications, what we use for the internet, which I'll talk about as well today. Okay, so moving on. So the physical layer, as you would expect, I said that before, it's all about the physics. Again, the name is so easy to remember. Physical physics. So that's why you need to have some background in physics. Not very advanced background. I would say very basic, high school level. You know, if you've done a computer science major, the least you could do is know what a sine wave is, what a cosine wave is. If you don't know basic trigonometry, I mean, honestly, it's bad. You need to review what they are, but it's very basic, because signals are sine waves. Your heartbeat is more or less a sine wave. You know, dude. If you went to a hospital and you saw your heartbeats, you would see that it's a signal. And that signal we can analyze. It has an amplitude, you know, meaning how high the signal is, you know, and it has a frequency. If you know before the exam, what happens to the frequency of your heartbeats? What happens before the exam or before a presentation? It increases. Yes, Sarah, yes? It increases, like do. That's the frequency, meaning the sine wave is kind of compressed now, right? If I increase the volume of it, that's the amplitude. And if I shift it forward or backwards, that's the phase. So I'm telling you these things because when I talk about it now, you'll be like, oh, I get it. I make an analogy with heartbeats. I make an analogy with sound. Anybody does music? Anybody does DJing? You know, like you put some music together and stuff? Anybody? If you've done any music in your life, you know what I'm talking about. You work with signals, because music is a bunch of signals overlapping, right? They overlap because you have, you know, like the background music, the guy singing. These are signals. Again, your voice is a signal. And again, if I raise my voice, that's amplitude going up. If I lower my voice, that's the amplitude going down. It's like volume in your car, you know, and your music. So try to kind of keep these in your mind when I talk about them in a second. Because if I give you equations, if I say sine 2 theta alpha beta gamma, people start panicking. Don't panic. Just know the basic foundation of it, because you need to understand the computer. There's nothing called zeros and ones. This is something humans made, because it's binary, because voltages are on and off, flip-flops. Your computer has registers that I say, on, off. The easiest thing was to say 0, 1. You know, we could have said 2, 3. They decided on 0, 1 because the binary representation is easier to kind of relate to. It's either true or false. So again, this is kind of a warm-up to what's going to come next, because I know a lot of you will panic once you start seeing waves and so on. But that's only one chapter. Then I'm going to move on to other stuff. But I want this course to give you all the tools that you need to understand what networking is. To program them, we have other courses. We'll teach you advanced system programming. But if you don't know the foundation, I feel very, very intrigued to come and say, you know what? You don't know much. Yes, you know how to call a function in a computer, JavaScript, Java. But to be honest, you don't know much, because I could easily play around with the stuff. So this is, and again, as a computer scientist, unfortunately, at Wollongong, you know, I was in another university before. We used to teach about 4 courses, 2 physics courses, 3 math courses, before I teach you computer. You know, because these are the foundation, and here we don't teach you much, unfortunately. That's why I want to take this course as an opportunity to actually give you some basic foundation. Okay, excellent. Excited? It's exciting, right? Anybody excited other than me?
Yes, Professor. It's
Okay,
very
yes.
exciting.
Thank you for those saying yes. It means a lot. Even if you're faking it, it's fine. At least you have some positive vibe. Okay. Okay, very good, very good. So back to this. We have 7 layers of the famous OSI, starting with the physical layer that deals with physics, deals with zeros and ones, deals with analog signals and digital signals. Again, don't panic. Analog are sine waves and cosine waves. Digital are zeros and ones. We call them step functions. It's very simple. It's like a square wave. It's not a sine wave anymore. It's like 0, go up, 1, go down, 0, go up, 1. So it's kind of, we call it a step. You know, we're stepping. Very easy. So digital, it's very similar to what you're looking at. This is a digital signal. Analog signal, as I said, is more like a sine wave. Again, that's fine. Why we care about this? Because we can change from analog to digital, and we can change from digital to analog. You see how cool this is? And anybody knows who does that? What machine does that? We use it every day. What machine is in charge of changing from a digital to analog on one side and analog to digital on the other side? No? Come on, it's a machine. It's a machine. DAC and CAD, these are not machines. Not a router. Yeah, what do? We have that. It makes toot, 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 toot. You used to do that. A modem, of course, a modem. So bonus point. So what does modem stands for? Modulator and demodulator. Modulator and demodulator. It modulates on one end and demodulates on the other. Because logically, the computer is digital or analog. Computer is digital or analog. Computer is digital or analog. Hello. Digital. The cable is analog or digital, typically. The most common cable, like the twisted pair. Yeah, it's analog. So something has to happen, right? Because it's digital data. I need to convert it into an analog signal. It's going to move on the cable. And then what would I do on the other end? The signal that I moved on the cable, I need to convert it back to, on the other end, I need to convert it back to digital data. Definitely. So on one side, I have digital data being converted to an analog signal. On the other side, I have an analog signal being converted to digital data. So when I WhatsApp you, I say, hello, that's a digital data. It's going through the wireless medium, typically analog communication. Typically, of course, we have digital communication as well. And then we end up getting the data on the other side. The receiver will get, hey, how are you? This is digital. So you could see the logic behind it. Okay. Very nice. Very nice. So physical layer, I think we got that. So we'll talk about it. We're going to have a whole chapter on this. Let's move on. So basic things they do in the physical layer. We're talking about what is the 0, what is the 1, how do I transmit it? Again, some questions we're going to answer. How many volts do I need for a 1? I mean, the most common would be high-low. The most common would be, you know what? If it's a 1, it's a high voltage. If it's a 0, it's a low voltage. That's the most common encoding. If it's a high voltage, low voltage. If I have 2 1s, it's going to be something like this. You know, for example, I have a 1, another 1, another 0. Again, that's common, but has a lot of problems, of course, because what if I have 5 1s? You know, if I have 5 1s, I would have like a signal like this. And that's not a good thing. That's not a good thing because I cannot keep track. How many 1s do you have? So I need something called synchronization. So do we have some problems? A lot of problems. So usually, let me be honest, the physical layer, people who deal with it are computer engineering. They deal a lot with the physical layer. The electrical engineering guys. Electrical engineering, computer engineering, they deal with it. But the computer scientists, they come and say, oh, I hope you know what you're doing. We're going to deal with the higher layers. I agree. But sometimes you cannot deal with the higher layers if you don't know the basics out of it, you know? And that's one of the kind of my strength. I did my bachelor's in computer science, my master's in computer engineering, my PhD in computer engineering. So combining these two made me understand, we need the foundation. At the same time, we know how to program them. Okay, and that's why I like you to understand a little bit physical there. So yes, some question we need to answer. How many voltage do we need for the 1s and the 0s? How do I establish a connection? how long should the bit time be? This is called the bit time. How long should it be? You know, because it's not synchronized, because the clock it's in microseconds. You know, if I mess it up by a microsecond, you will get 2 ones instead of 3 ones, because it's not 100% synchronized. And that's a problem. You cannot say we have a clock. The clock doesn't work because it's not accuracy to a microsecond. And that's one of the problems that we face. So how long is it? How many pins do I need for the connector? You have to remember the connector that you have. We have a USB now, but if you have a serial connector or a parallel connector, you know the serial for the printer or the old printers, you have pins, right? You know what I'm talking about? The pins that come out of it. Sometimes you have, 16, you have 32 pins. These pins, typically, they used to represent, each one of them used to represent what? What do you think? Every pin used to represent what? When I put a cable that has pins in it, what do you think these pins represent? Okay. What do you think it represents? Just what do you think? I mean, it's fine. Just you could guess. Yes. I mean, not ones. I mean, typically close enough. A bit. Yes. Thank you, Danny. Typically, they represent bits. If I was sending 10011, every pin represents a bit. That was the logic behind it. Plug them. If I have a byte, that would be 8 pins. I would have 8 pins in it. That's the logic behind it. Obviously, they're obsolete. Mostly obsolete, meaning they're not there anymore. Obviously, because we're using USBs and HDMI and so on, which kind of changed the whole design. Again, especially if I'm using digital communication. So, but yes, how many pins? How long the bit should be? How many wires do I need? Should I use electrical, optical, or waves? Again, waves meaning wireless, optical meaning fiber optics, electrical meaning obviously the normal electrical signals that we use. Okay? So very good. So let's move on. So we got the physical layer. So physical layer is all about the physics, all about zeros and ones, about voltages and so on. We go one layer up. Now we're not talking about bits anymore. We're talking about frames. So you can see the unit change. So the data link layer basically says, you know what? We cannot deal with bits. I mean, I cannot do much with bits. 0, 1, 0, 1. Let the physical layer do these things. The data link layer says we're going to bundle them together. And when we bundle a bunch of bits together and add stuff to it, to do error correction and error detection, we call it a frame. So data link layer, in simple terms, it has one job. The job is take these bits from the physical layer, put them together, in an envelope, and call it a frame. And not only this, why do we do that? So that we could add a checksum and add a header to it. And these are things that we'll be doing calculations on the frame itself to know if something happened to the frame. Hence, something called error detection and something called error correction. Another big thing of the data link layer is something called the Mac. Not the Big Mac from McDonald's. Okay, I think you guys know what the Big Mac is. The Mac is different. Anybody knows what it stands for, the Mac? If you Google it now, you're going to get Big Mac from McDonald's. Yes, Reda, well done. MAC stands for Medium Access Control. Did you Google it or you knew it? If you knew it, well done, bonus point for you. So, Medium Access Control. Medium Access Control, meaning it allows to control who accesses the medium. Again, if I have 5 people fighting for the medium, the MAC layer, which is a sub-layer of the data link, very important. The data link layer has 2 sub-layers, actually something called LLC and MAC, but let's focus on the MAC, that's the most important. The medium access control, it's all about giving access to the medium, especially if you're in a local area network. We don't want to send all at the same time. We're going to have collisions. Our packets will collide. So the MAC is doing all that magic. So it's a sub-layer of the data link. So if you go back to what is the job of the data link, it has basically, for me, 2 major jobs: error detection and correction, meaning knowing if something happened to the frame in between me and you, and try to detect it first and try to correct it if we can, using something called having code and many other protocols. The other thing that it does is, as I said, medium access control. It controls the medium. And we'll talk about MAC layer protocols. A famous MAC layer protocol is, anybody knows? Famous, actually the famous in your generation. We use it every day, every minute, every second. Using it now while we speak. I'm using it. The famous medium access control is what? Protocol. I like when I do this and I don't get the reply. People are Googling. Yalla, Google, Google, help me Google. That silence, yeah. Awkward silence. I hate awkward silence. I don't know. It's fine. If you don't know, it's okay. You can type I don't know. It's totally fine. You use it every second. You cannot hear me? Not internet? Medium access control. You want to access a medium. I mean, again, you just keep Googling and give me terminology. You're using it every second. What are you using now on your phone, on your mobile phone? What do you use?
Internet.
Wi-Fi. Server. Thank you, God.
Okay.
And it took you a lot of time. Wi-Fi. Of course, Wi-Fi. And Wi-Fi is IEEE. Yes, you get a bonus point, Sarah. I like this. Wi-Fi. Do I get the bonus point? Immediately after she answered. Of course you do. Is somebody keeping track of bonus points? Brooke, Mr. Brooke, are you there? Okay, Afrozali, I think I could trust Afrozali, yes. Thank you, Afrozali. You're keeping track? Thank you. So yes, it's Wi-Fi. So Wi-Fi is IEEE 802. Are you happy, Sarah? You got a bonus point? Well deserved. Are you happy? Excellent, excellent. Okay, Brooke, thank you for replying. So again, by the way, sometimes I ask you questions, obviously not to kind of kill time. I want to wake you up because I like when I ask and somebody replies, even if it's something you don't know. I like when somebody says, I don't know. I like it. It means that you're with me, you're attentive, but you don't know. Total respect, you know? Chapeau bas. However, what I don't like is those who are just logging in and taking a nap, waking up after 2 hours, you know? So this is the idea behind it, okay? So I want you guys to really come and interact as much as you can, even if you don't know. So thank you so much. Yes, IEEE 82.11, the famous Wi-Fi. The famous Wi-Fi protocol is a MAC layer protocol. It's called IEEE 82.11, and you have different versions of it. I will be talking about it later on. So data link layer, yes. Physical layer to network layer. The communication in between will be the data link layer. And these are the things that's in charge, okay? Let's move on. So data link layer, so yes, things that we look at, errors is something very important. We deal with data frames. As I said, we're not dealing with bits anymore. Again, damage, duplicate frames, lost frames, all these things. Flow control, we've talked about flow control before, meaning I have a fast transmitter, a slow receiver. You remember flow control? I've talked about it before, yes? Flow control, fast sender, slow receiver. We said one of the solution was what? The most common, which is not a good solution, but at least it solves it. How do we solve flow control? The simplest solution. Slowing down the fast receiver. Thank you, Rafif. Thank you, Rafi. Thank you. Thank you, Bida, as well. Yes. So flow control we've talked about before. So all these are part of what the data link layer does. Again, it looks at simplex, duplex. How do you control? As I said, the MAC. It's all about the MAC here. Is medium access control. Okay, very good. Okay, as I said, the MAC layer. So far, we've talked about the physical layer, data link layer, hop by hop. We're jumping, as you could see, within the subnet still. We are still within the subnet. The data link layer gives information to the physical layer on one end, and the other end, the physical layer gives information to the data link on the other end. And hop by hop, I'm jumping from physical data link, one more layer within the subnet, which is the network layer. The network layer, as you expect, the most important thing, first of all, the unit changed. Before we were dealing with frames, now we are dealing with, we're not dealing with frames anymore, packets. Excellent, excellent, thank you guys, love it. Packets, we are dealing with packets. We moved from bits to frames, from frames to packets. Again, you say, what is the difference between a packet and a frame? Not much. Ironically enough, not much, other than the header and the checksum that we might add to it. So if you think about it, so if I had a bit here, this was a bit. Then I converted it to a frame. When I bundled them together, it became a frame. So this is a bit. A bunch of bits becomes a frame. And then when I come and become a packet, you think about it, it's still a frame. It is a frame. But basically all I did is added stuff to it. You know, I mean, I didn't do much other than add maybe a couple of things together. And this is now, we call it a packet. So a packet is a frame, but in a language that the network layer will understand. Typically, you know, we're talking about addressing, we're talking about, you know, IP addressing, if you're talking about the internet. So a lot of other stuff that we did not care about too much. So if you think about it, the data link layer focuses more on a LAN within the local area network. So I'm not dealing with IP addresses yet, if I'm talking about the internet. I'm dealing with the MAC address here, most likely. When I go to the packet, I'm dealing with the internet, so we're dealing with the WAN here. We're dealing with the WAN. So when I'm talking about the wide area network, I need more information. Hence, I'm adding the IP addressing. I'm adding a lot of other information too. I'm adding routing protocols. You know, routing me, I need to know how to go, what's the optimal path, and so on. So therefore, the packet is more information in it compared to a frame. Okay? Yes, the frame and headers, if you want to call it, again, many that will allow me to optimize the delivery of the packet. So what do we do in the network layer? It's all about routing. So these are the things, again, the network layer, we always call it the boss of the subnet. So it controls the operation of the subnet. So this subnet that you look at, again, the sub network, we'll be talking about subnetting where we do IP addresses. You know, what does subnet mean? You know, when I come up with an IP address and so on. So keep that in mind. So the network layer is the boss of the subnet. It is in charge of routing, congestion control. So we're talking about traffic here. You know, traffic. We're talking about addressing, as I mentioned, especially if I have heterogeneous networks, meaning different kinds of networks. How do I address them? How do I make sure that you understand what I'm saying? How do I know what your address is? It's like me shipping something from Dubai to Chicago. To ship it, I need to understand what kind of zip code they use and addressing they use, right? These are heterogeneous networks. The network in Dubai maybe will be using, I don't know, Aramex. When I go there, I'd be using FedEx. So we need to really understand terminologies in terms of what kind of addressing, what kind of services they offer and stuff like that. So what kind of rules they have in the country compared to what kind of rules we have in Dubai, in the UAE. So addressing is very important, you know? So what does a network layer does? What does it do? One, it controls the subnet. Two, is in charge of routing. Maybe that's not number one. Network layer is all about routing. To be more specific, routing protocols. You know, how do I find the optimal path? And optimal doesn't mean shortest. If I want to do the shortest, it's easy. We use something called Dijkstra, right? Or Bellman-Ford. These are famous algorithms that we taught you in graph theory. They should have taught you this in data structures or computer programming, basic stuff. However, when you do routing, it's not always about the shortest path, obviously, because of, why is routing not always the shortest path? Because of, I think there's a delay in my questions, maybe. Because of congestion. Thank you, Abdullah. It's fine. Because of congestion, Rida. Thank you. Because of congestion, because of traffic. Yeah, it's like me driving my car to Abu Dhabi. If I want to take the shortest path, it might be Sheikh Zayed. But there might be traffic. There might be an accident on Sheikh Zayed. What do? I take, I don't know, another route, which is longer, but overall less time. So it's optimal. It might cost me more money because I'm paying more gas for the distance wise. So you can see there's a lot of factors when we talk about routing protocols in internet or any network. It doesn't have to be internet, huh? So it's all about the optimal. And optimal is a very kind of vague. So how do you define optimal? You can define it in many ways. It could be the least cost. It could be the least time. Sometimes the least time means the least cost. Sometimes it doesn't. Depends on how you look at it. Okay? Very interesting. Let's move on. So again, obviously, if I'm broadcasting, we don't need much about the network layer. Where do we broadcast? Most likely. Do we broadcast in a WAN or a LAN? Do we broadcast in a small network or in a large network? In a LAN. Yes, Abdurrahman, bonus point for you. Well done. We broadcast in a local area network, 100%. In a small network. I mean, obviously, because you cannot broadcast in a big network, you will have tons of collisions. Doesn't make sense. So you can see that's why we don't need, that's why, now we know, that's why we do not need a network layer within a LAN. That's why within the local area network, we deal with the MAC. You know, the MAC address. We call it the MAC address. We deal with that. We don't deal with the IP address because of that. These are so important things you need to understand. These are things you cannot Google or YouTube. You know, how does this work? You need to kind of really understand this concept. And that's why we teach you, you know, for you to kind of think more than the obvious. The obvious is there. We could YouTube stuff. But let's think about, why did we do that? Why do we have a MAC address in a LAN? We don't have it in a WAN. We don't care about it because of what I'm saying. Okay? Perfect. So now we are done with the subnets. You can see subnet, physical data link, and network. We go 3 layers down, 3 layers up, 3 layers down, 3 layers up until we come to the destination. And most likely in the destination, I will have more layers here. You know, I will have more here and more here. Peer-to-peer will have more. In between, I only focus on the subnet. Okay? Perfect. So we have hop-by-hop delivery for the physical data link and network until we come to the destination where we have all the layers. It could be 7, could be 4, could be 5, depending on the protocol stack that you're using. So now we go 1 layer up. Again, we have the transport layer, as you would see, and the other layer. So what does the transport layer does? Again, the unit changes a little bit. Now we're using something called PDUs, protocol data units, you know. Again, something we'll be using again and again, but typically, same logic. I'm going to take the data from the network layer. I'm going to add stuff to it and give it to the session layer. The most important job of the transport layer is process to process. Very important. Process to process. Okay? This is very important. Why? Let me tell you this. The job of the network layer, the guy before him, this thing, is to make sure that the packet goes from one end to another. So I receive a packet here. It goes from one end to another. It does not guarantee that it goes to the exact process that requested it. You remember when I did it last time? I said in my computer now, what do I have? What are things running in the background? What are the things happening? What do we call them in computer terminology? Last week we talked about it. What do we call them? Applications, which are processes, right? And processes have what? PIDs. Yes, perfect. So we have a lot of processes. And these processes, again, could be the email, my Outlook. It could be, you know, WebEx. It could be Zoom. All these are processes that I'm running. I could do them in parallel. And many of them are being run, whether you like it or not, we call them background processes. The problem is these processes are all connected to the internet, right? And they're making requests. So what happens is that on one side, I have all these processes. Let's call them P1, P2, P3, a whole bunch of them, right? Remember? Let me just show you, remind you. Let me just show you. Control Alt Delete. Task Manager. Let's see how many processes I have in my computer now. Here you go. Remember, we said, again, these are all the applications running now. Again, typically all these have processes. You can see how much memory they're taking. If you go to details, you see, these are all PIDs. These are all the processes. Look how many. These are all processes. Again, obviously from the command prompt, you can actually look into these processes. All these processes are basically applications, or within the same application, you have other processes doing stuff. And these are all running in my computer now. You can see. So when on one end, all these are doing what? Who could tell me? All these processes are making what? They're making what? They're making what?
Like they all have functionality.
Okay, they're making for what? For the internet, they're making requests. Thank you, Muhammad. Requests. And typically, if you're making requests, you expect, right? What do you expect if you're making requests? Obviously, you expect a reply. Again, using the networking, so you're going down, going up, and so on. So what will happen is many will come back, right? All of these are using the same what? They're using the same what? Same what? They're using the same
system.
They're using the same, what kind of address? I'll help you out. The same
MAC
IP,
address.
which is the computer IP. The network IP that I'm connected to, right? So they're all using the same IP. The problem is the network layer will guarantee that all the replies come back in an optimal way. But it doesn't know which one is for whom, right? So it doesn't know which one is kind of coming to which process. So the network layer guarantees that the packet that left gets to the destination, but the network layer doesn't guarantee that it goes to the process. Who guarantees that? Who knows which process asked for it specifically? Who knows what layer? The transport layer. Thank you guys. Now we know, you see? It's very interesting. So let's go back. So yes, the transport layer, it's all about the specific process. It's all about ensuring they arrive in order, meaning if I send ABC, you get ABC, not CBA or BAC. So it's all about flow, order control, process control, process addressing. We call it an end-to-end protocol. You see? The end-to-end protocol. So transport, it's all about end to end. It doesn't care about what's happening in between. It's end to end. It handles retransmission. So if something got lost, it actually retransmitted. It handles duplicates. So there's error correction as well. It handles flow control as well. So also has flow control. So what do you notice here? Where did we talk about these before? Where did we talk about these? Transmission, duplicates, error. Where did we talk about them? We said somebody else is doing them. The data link, thank you. The data link. We already talked about it like 10 minutes ago, you know? The data link, yes. So data link layer already does many of these. And this was one of the bad design issues of the OSI. If you remember when I started the OSI, I told you they claimed that every layer does a specific job. However, it turned out that there's a lot of overlap. Some of the layers are doing the same thing. Some of the layers are doing a lot. Some are not doing much. So that was one of the critiques that I'll talk about quickly towards the end of this part of the lecture. So yes, one of the bad things of the OSI was some layers replicate what other layers do, and some layers don't do much, and some layers do a lot. You know, these are kind of the major downfalls of a specific design flaw in OSI. Okay? Okay, as I said, flow control, duplicates, these are things that we already talked about, but most likely the most important job of the transport layer is process to process. End to end. You know, that's kind of the highlight of the transport layer with the other things that they do. Okay, so again, network is host to host, and transport, again, this is host to host, and this is process to process, end to end. Okay, end to end. Very good. So now we come one layer up. So we talked about the physical, data link, network, transport. The next layer in the OSI is something called the session layer. And I say something called the session layer because That was also one of the bad things about the OSI is the session layer doesn't do much. They came up with something called session control, dialogue control, and synchronization. They said we need a layer to be in charge of establishing sessions. You say, what is a session? To be honest, even they don't know what a session is. When they came up with it, they were more like, oh, you know what? Session is when we don't establish a connection. Let's think about a session as maybe multiple connections, or think about a session as a connection for a long term. So session is not really well defined. Long story short, however, the session control said, if you want to establish a dialogue, again, what is a dialogue? Again, not well defined. And again, that was one of the big pitfalls of the OSI. That's why TCP/IP said, you know what? We don't care about session. Let's kill the session. There's nothing called the session. So session, by their definition, was all about dialogue control, meaning I could allow simplex, duplex, and so on, something we already had a little bit of in the data link layer as well. Even in the transport layer, we have something like that. So the idea is to clean up everything from the transport to the layer on top of it. The idea was to provide synchronization, to make sure, you start here, you end here. I mean, that's very common for if I'm downloading a big file. If I'm downloading a big file, let's say 5 gigabytes, and internet got disconnected. Back in the days, what used to happen? What used to happen, even now, in many different areas, if I'm downloading a big file, I came to 4 gigabytes and disconnected. The internet got disconnected. What will happen, typically? Yeah. It will pause, and then I connect, it will continue, right? Who made that? Typically, there are two things that might happen. It might pause, I connect again, and I continue where I stopped. Or it would say, you know what, start all over again, right? It will cancel the download. So most likely it will cancel the download. Again, the idea of the session layer, was to take care of this, more likely, is to establish a session, make sure I'm synchronized, and if anything happens in between, I could continue where the session got interrupted. So it's no longer a connection. Now we are establishing a connection. If I cut the connection, I lose everything. If I establish a session, we could think about it that, you know what, we could continue where you kind of stop. But it's very difficult because you have to remember, these things are coming. They might be coming out of order. Things might not have come yet. So I could lose track. So it's not as easy as it sounds. However, the job of the session layer was exactly this, to establish a dialogue between senders and receivers, and something called token for floor control, who wants to come next, and how do I establish traffic in one direction or both directions. Again, I say it slowly because it's not a layer that really got a lot of attention, and it's a layer basically that people got rid of over time, and they kind of embedded what it does in other layers. Because if you see, physical layer does a lot of work. Data link layer does a lot of work. Network does a lot of work. Transport does a lot of work. Session, not much, you know. I mean, yes, it does a couple of things. We could have easily embedded it in some other layers. And that's why you will see later on, we don't have a session layer. So the next layer, again, another critique of it, is the presentation layer. The presentation layer, again, doesn't do much. As the name sounds, it's in charge of presentation. How does the data look like? So some things about the presentation layer included encryption, maybe encoding, more likely. Encoding my data, compression. I want to compress my data. It's these with size issues and so on before we get to the application. So the presentation layer is I need to encode my data, translate it in a way, compress it, encrypt it. All these things were in charge of the presentation layer. It has some functionalities to give it, to be honest. So it takes from the session layer, gives it to the application layer, and does these things in between. So we're talking about syntax, semantics, formatting of my data. Again, am I using ASCII code, Unicode, compressing, encryption? All these are part of the presentation layer. Again, this is one of the layers that also faded away, you know, because Where do you think these functionalities were added to? These functionalities that you're looking at, encryption, compression, what layer? What layer do you think does that now? Come on, what layer does that? Where did we killed, typically the presentation, we killed it, but who does the compression, the encryption? What layer do you think does that? Common sense. No. Go up. Go up. Come on, guys. Presentation. This is called presentation. Yes, application, of course. Application. I mean, come on. The application itself is doing these. You're compressing, decompressing, encrypting. So the application layer is doing these. That's why I said, you know what? I don't think we need a presentation layer. Why don't we make the application layer take care of this? That's why, again, the presentation layer ceased to exist typically in most network designs. They said, you know what? We have some functionalities, we agree on them, but we could combine them with other layers. So finally, we come to the application layer. As you would expect, the application layer is the actual application protocol. So if I'm doing web browsing, what would the application protocol be? If I'm doing web browsing, what would the application layer protocol be? If I'm browsing the internet, HTTP, thank you so much. If I'm uploading a file, what protocol do you think is going to be? If I'm uploading a file, most likely FTP or a variation of it. If I'm emailing back and forth, what protocol would you think will be? Application layer. If I'm emailing, you do that when you configure your email. What protocol? If I'm emailing, SMTP. Thank you so much, Harsh. Bonus point for you. SMTP, simple mail transfer protocol, most likely, or POP3 or other application. So you can see the logic. So now we are at the application. We're dealing with these application layer protocols. The actual application, if I'm zooming, like using Zoom, I'm doing WebEx, I'm using a specific protocol, of course, you know. So obviously in the transport, we talk about TCP, UDP protocols, and so on. In the application, we're talking about the actual protocol, okay? So again, FTP, HTTP, Telnet, and so on. I could keep on going. I'll give you some examples as we go on. So to summarize, these are the layers, as you can see. The physical layer, data link, network, transport, session, presentation, and application. Again, each one has a job. I already talked about each one of these, okay? So these are within the subnet. These are some examples. I showed you some examples here. So the transport, we talk about TCP IP. In TCP IP, what they did, they came and said, you know what? These are important, but we're going to combine them to one. They called it the network interface layer. So the physical and the data link in TCP IP, the one used for the internet, got combined. They called it the network interface layer. The network layer stayed the network layer. They just called it the internet. The transport layer stayed the transport layer. Again, more famously known as TCP. And finally, here they said, you know what? This is batata. This is batata. We don't need this. We don't need this. We're going to combine all these three together, and they called it the application layer. Okay? So you could see TCP IP said OSI is okay, but there are a lot of mistakes in OSI. So why don't we go and combine stuff? So instead of having 7 layers, how many layers does TCP IP have? How many layers does TCP IP have? 4. Okay? So we have 4 layers, as you can see. We combine layers together. Again, TCP IP, one more time, is the internet, just in case you're wondering, is what we use over the internet. We have other protocols that we use different. That's why we want to teach you the foundation, because you could use different than TCP IP. One more time, as I said, IoT, Internet of Things, which is the most popular smart cities. We don't use TCP IP because of many issues with it. So you could design your own network protocol to work on over the internet or over using tunneling and other technologies. Okay, so yes, examples one more time. If I'm talking about the physical layer, data link layer, if you combine them together, we're talking about Ethernet, token ring, you know, ATM. It's not the ATM machines, okay? ATM networks, okay? So ARP, address resolution protocol, we're talking about the network layer. IP, that's the most famous internet protocol, okay? IGMP and ICMP, you know, internet control messaging protocol. That's very common, like the ping. The ping, we all know the ping, right? The ping. When you're doing pinging, you're not sending an IP packet. When you're pinging, you're not sending an IP packet. What are you sending? Anybody? You're not sending an IP packet. You're sending a you guys, I actually point. I just said it now. Just pay attention. That's all you have to do. By the way, when I ask a question, thank you. Did you Google it, Basim? Okay, okay. But when you take time to answer, I just have some doubts. Okay, my bad. I believe you. I give you the benefit of the doubt. Okay, so bonus point for you. But please, if you want to get a bonus from now on, it has to be instant answer. Otherwise, I won't give you the bonus point. If there is a delay, meaning there's something happening. You either know it or you don't. Of course, ICMP. Okay, ICMP packets. Again, internet control. You're sending that to do some stuff. There's small packets to do some controlling. So it's very interesting, you see, to understand this. TCP, UDP, these are famous for transfer protocol. Again, we'll talk about them when the time comes. I just want to give you some ideas. Again, in the application layer, we're talking about FTP, SMTP, Telnet, and many others. RIP, what does RIP stand for? What does RIP stand for? You know RIP. Okay, so no bonus point anymore. Yeah, rest in peace. Huh? Okay. I thought people would say rest in peace. Okay, so again, no bonus point if it takes you time, obviously, because you Googled it. So please, if you don't get bonus points from now on, it has to be instantaneous. Otherwise, I will not accept it. Okay, so we'll talk about that as we go on. But I wanted guys to say rest in peace. So I wanted you to do that. Okay, so let's move on. So really quick, now again, the rest, you know, let me just exit this real quick. I'm not gonna basically, I'm gonna fast forward on these, but just for you to get an idea, I'm gonna fast forward now real quick because these are more like things you need to know so that we could kind of end the part one of today's lecture. But just real quick, why did OSI not win? For many reasons. I'm not gonna really spend too much time on them. But typically, they had bad timing, bad technology, bad implementation, and bad politics. These are the reasons what led to, yes, politics meaning they did not work well with the government. And politics is a big important thing when you talk about technologies. So there's something called the apocalypse of the two elephants. You could see here. So we do any famous thing that we do, typically, here you see we do a lot of research, we come up with standards, and then we do $1 billion investment. This is what we refer to as the apocalypse of two elephants. So any kind of famous technology looks at this. So the problem with OSI, they spend a lot of time doing research, a lot of time on this, which led to failures here. They didn't have time. By the time they want to come up with standards, somebody else took over. So bad technology, their specs, you could see they're very confusing. Many layers didn't do much. Many layers did a lot of stuff. Bad politics, they were not pushed by the government. They did not align with the government. So again, it's a flawed model, had too much information. It was 7 layers just because somebody woke up and said, you know what? IBM at that time had something called SNA. And they said, you know what? They had 7 layers. Why don't we also have 7 layers? That was one of the reasons why we have 7 layers, which is kind of a stupid reason. So some of them were very complex layers, some were not, as I said. So long run, it was a bad technology. Bad implementation, bad implementation. When they started using OSI, there was kind of a kind of synergy saying, you know what, if you're using OSI, it's bad quality. You know, it's like how iPhone approached quality. Said, if you have an iPhone, it's good quality. If you have, I don't know, a Samsung, initially, it was bad quality. So this kind of illusion of quality. And OSI, exactly this is what happened to OSI. When people started using it, they said, you know what, OSI is bad. And this quality thing was reflecting on it. However, TCP IP did a partnership with what? With Berkeley. In case you don't know what University of Berkeley is, one of the leading universities, they said, you know what, let's partner with Berkeley. And this kind of eluded quality. quality, therefore people loved it. And that's what the internet became, based on TCP/IP. I mean, these are things for you to think about later on, but it's important to say, you know what, I know how OSI works. I know it's a good thing for teaching. It's not a good thing for implementation. And that's what TCP/IP became. They tailored with something called Berkeley sockets. Bad politics, as I said, TCP/IP when it came out, because you have to remember, these two are competing. OSI had 7 layers, TCP has 4 layers, and they did not do good politics. They did not do good partnership. TCP/IP partnered with what? With Unix. And Unix is kind of the leading operating system when it comes to engineers and efficiency. However, OSI did not do that, so their standard was inferior to what TCP/IP was offering, which was already part of Unix. So, really quick, how did we look at OSI and TCP/IP, comparing them? Internet started as something called ARPANET. ARPANET is what was developed by, again, ARPA is the Department of Army in the United States. During the Cold War, the Department of Defense said, you know what, we want something to connect all our things together. And DARPA came and funded a big project on this. They started using circuit switching and something called IMPs, which is interface message processors. These IMPs are connecting these computers together. And again, the packets were kind of small, 8,000 bits of message. They had some rules to do, and they used to connect using 56K kilobits per second. Okay, so just for you to understand how the internet evolved, it's kind of nice for you to see how it kind of started. You can see it started something like this, how the telephone looked like. This is how the telephone looked like. They started saying, you know what, this is the telephone. Why don't we connect these things together, you know? Let's try to connect them together and get something like this. That's what we kind of refer to the ARPANET. Again, this is before the internet, one more time. Funded by the Department of Defense in the United States. To be more specific, something called DARPA, which is related to the Army. They wanted to connect the computers together. They said, let's start doing it. Started doing it. They connected multiple computers together, as you can see. Is my voice better now? Can you hear me? Okay. So the original ARPANET uses something called, as I said, IMP protocol. They call it IMP protocol. It's very basic. You know, this computer was connected to this computer. Let's start with small universities. And look how nice. I love this. I love this diagram, by the way. UCLA, University of California, Los Angeles, Utah, you know, Santa Barbara. You can see it's all California here. Okay. They said, you know what? Let's connect these together. Then they said, you know what? We're going to add MIT. Then we added others. Harvard jumped in. Then you could see how it evolved, right? It started so basic with 3-4 universities, added another, and started growing. That's how the ARPANET started. We funded this project that started really as so small and really changed humanity as we know it, you know, and this is how the ARPANET later on became the internet. Okay, so the internet, hence what we refer to as TCP/IP. TCP/IP, we have 4 layers: host to network, internet, transport, and application, which I already kind of talked about. Again, I'm going to fast forward a little bit. So layer 1 is a combination of physical and data link. Layer 2 is a network. Layer 3 is typically the transport. Layer 4 is a combination of all these 3 layers. Okay, so you could see if I look at TCP/IP, has 4 layers compared to 7 layers of the OSI. Again, if I compare the layering of every layer in the TCP/IP, what they do, again, the internet layer in TCP/IP, typically it's connectionless, meaning I don't establish a connection. When I talk about the internet layer, we could go on different paths and so on. We use the IP protocol, and we can deliver at the other end. Again, obviously, I'm using packets. If I look at the transport layer, it's end-to-end. The 2 famous protocols is TCP and UDP. TCP is connection-oriented, so I establish a connection. It's reliable. It's a byte stream, meaning I'm sending bytes. UDP is what we refer to as user datagram protocol, and I like to remember the U as being unreliable. These are the two famous protocols. So it's unreliable, it's connectionless, meaning I don't care about quality as much as I care about speed. So UDP, it's all about I'm unreliable, but I give you better speed, better delivery. Okay? Again, the application layer, we already talked about it. So just to summarize this part, again, host to network is what we defined as the physical and the data link. But you could see TCP IP really focuses on two major layers. What are they? It has 4 layers, but 2 layers are doing all the magic, which are in TCP IP, the name says TCP IP, TCP IP. So the 2 layers are, it's called TCP IP. So the 2 layers are the transport and the network. Thank you so much, Sarah. Bonus point for you. TCP, which is the transport, IP, which is the network. So you can see TCP IP was all developed around these 2 layers. Yes, we do have 4 layers, but you could see that the other layers are not as much useful. Okay, so let me stop here for the first part of today's lecture. Second part, I will finish these different kind of addressing and start the physical layer chapter. Okay, any questions for me?
Yes, Professor. There was one slide you were talking about the Cold War. I didn't
Any
understand
questions?
Yeah, Professor, can you hear me?
Okay, so that was, again, remember, what I just did now was a continuation of what I started last time. And I kind of took my time doing it last time. And I see how it goes today to see, hopefully, we can move on. Okay, so let's do the quiz now. We're going to do the quiz, take a 5 minutes break, come back, maybe a seminar or 2, and then continue with the lecture. Okay? Yes, what's your question?
Hello, sir, can you hear me?
What's your question? I cannot hear anything. Are you talking? I cannot hear you. Okay.
People can hear me.
Let me just see what's happening with my. Okay, can you talk now?
Testing.
Yes, go ahead.
Hello, yes, Professor. In that slide you showed about the Cold War, I didn't understand one part. It said that the work is funded by the people or something. I didn't understand that part. What does that mean?
Work what?
The Cold War, it said in the same line is funded by so and so. What does that mean?
The Cold War?
Yeah, you were talking about one.
Don't worry about it. That's fine. This is a history lesson. You can Google it. Let's focus on networking, my friend.
Yes, all right.
Okay,
thanks everybody for letting him know.
Okay. Anybody else? Networking related questions? Okay, that's fine. Let's start the quiz. Good luck. We're going to start the quiz in 1 minute. Please go do the quiz. It's an easy
Professor,
quiz. Yes, Abdullah.
can I ask you a quick question?
Yes, please.
Can we call the transport layer and the data link layer host to host and end-to-end layer?
One more time.
Can we call the transport layer host to host layer?
The transport layer host to host?
Yeah.
Yes. That's what we said. Remember, end to end. No, host to host is the internet. Host, hub by hub. The transport layer is end to end or process to process. The internet guarantees that your message comes to the host. The host is my computer. That's the internet job. It's host to host. Once it comes here, the transport layer needs to make sure it gets delivered to the process. So it's process to process or end to end.
Thank you so much.
Thank you, Abdullah. Thank you. Good question. Okay, let's start the quiz. Yalla, good luck. You have 10 minutes only because it's an easy quiz. Good luck. Thank you, Yusuf, always reminding everybody of the link. I'm going to start the quiz now. I'm not going to wait anymore because I gave, time for you guys to join the lecture. Good luck. You have 10 minutes starting now. Good luck. It's going to start in exactly 10 seconds. I'm starting it. So it started. Good luck. 10 minutes starting now. So it's 11:48 now. I'll give you till 12:48. So I'll give you till 12:50. It's fine. I'm going to give you 12 minutes. 12:50 quiz ends. And just to clarify, after the quiz, you can take a 10 minutes break till 1 p.m. I will see you at 1. Oh, sorry, I think there's 11:50. Sorry, my bad. I went till 12. 12. No, okay. Sorry, my bad. 12. 12:10. Okay. Till 12:10. 12:10. You cannot delete messages, right? Okay.
Sorry, Professor. Can you?
Okay. So we're back here. So towards the end of this lecture. So we talked about OSI, TCP/IP, different layering, the needs for the layering, the job of every layer, and we'll talk about more about each specific layer as we go on. So again, one of the things that will come across is addressing. So when we're addressing, you notice that layers work and do different things and work with different things. Hence, the addressing, how I address, is different from one layer to another. So the typical addressing techniques are, I either use the physical address, the logical address, the port address, or maybe some kind of specific addressing. Let me just show you. So the physical layer, as you would expect, I'm looking with the physical address. I'm dealing with the physical address, the actual physical address. When we go up, we're talking about IP addressing. This is what we refer to as logical address. You know, it's not a physical address anymore, it's logical. Most likely, it's the thing that's connected to the network. When we go to the transport layer, obviously, as you would expect, we are dealing with the port address. Because I'm dealing with the port address, as you see, the PID, more or less. I need to know what specific port, what specific process ID is working at what specific port. So the port address is very important. And then you have finally the specific address, which is the process working there at the application. So if you see, my process works in a specific port. The process is working at a specific port. And obviously, my IP address would lead me to the port. And we start with the physical address. Typically, when we're looking at a LAN, most likely we are focused on the physical address. Very important to know the difference between physical, logical port, and specific addresses. Okay, each one have their use in specific layers. Let me give you some example. So in this case, we have a physical layer. It's a different color. So we have a physical address of 10. Sends a frame to a node with physical address of 87. So we have this guy is 87. That's the physical address. Let's call it PA. The physical address is 87. And you have the sender has a physical address of 10. So we're looking at the physical address. Most likely we're looking at the local area network here. And I'll give you, obviously, the physical address is not usually a number like this. I'll give you the format of it. Okay, and in this case, we have a bus topology, and they're sending to each other. You can see how simple. One more time, I have my data. This is my data. I could add some trailer to it to get some more information, but typically what I care about is this. You have the sender address, you could see 10. The receiver address is 87. You can see the format. So 10 is sending to 87. So when this guy leaves here, it has who's sending it and who's receiving it when we're dealing with physical address. Very simple. Okay? And obviously in between, you see, it went through others that ignored completely. because I'm within the LAN, I'm broadcasting, there's no routing here. And then I come to the other end. That's what happens in a local area network. If two computers are connected in a LAN, basically they're communicating using the physical address communication. Okay, let's move on. How would the physical address look like? As you obviously you should have seen this before. It's typically 6 bytes. You could see it's 6 bytes. Looking at 12 hexadecimal digits. So 6 bytes, 1, 2, 3, 4, 5, 6. So we have 6 bytes. And this is how the physical address of any computer is. Okay? So it's 12 hexadecimal digits. Every byte is 2 hexadecimal digits. Okay? And separated typically by a semicolon. By a column. Let's see. How do I get the physical address? How do you get the physical address? Very easy. We can go to command prompt. Okay? You all know how to go to command prompt, right? So let's go CMD. Right click. Run as admin. Yeah, sure. So let's see. So if I do ipconfig all, if I do ipconfig all, you could see I could find my physical address. You can see it. Okay, this is for the LAN. Could go, as you could see, the physical address of the Ethernet adapter. Yeah, you can hack me 100%. Try if you can. LAN adapter. You can see we have the physical address. You can see physical address is for many things. It's not physical address of one thing. Again, the Wi-Fi adapter, you can see it as well. The physical address. So again, the physical address, as you could see, is very simple. Used within a local area network. It's useless, by the way. Useless for you guys from outside. It's basically within the local area network. That's why we need the physical address. Let's see the other kind of addressing. Again, one more time, 6 bytes. That's what you need to remember, you know, and typically these are hexadecimal. You know, we have binary, you know, we have octal, we have hexadecimal. That's the representation of it. Now, let's take it one level up. We have local area networks connected to each other. So I have LAN 1, LAN 1, LAN 2, and LAN 3. Within these local area networks, you can see things are happening. So we have 2 routers connecting 3 LANs. So router here, router 1 and router 2. They're connecting 3 LANs together. Again, each device has a pair of addresses now, not only 1, 2 addresses, logical and physical. Again, we're connected to one link. Obviously, the network itself is connected to 3 networks. You can see, so we have 3 pair of addresses because I'm connected to 3 networks. So one more time, let's look at router 1 really quick for you to understand what I'm saying. Because I'm connected to 3 networks, so it's connected here, and connected to the 3rd network, then I will need an address for every network. So you have to remember, the logical address is for the network. It's not for the actual physical entity. Unlike the physical address, it's for the actual thing. So if I'm connected to the network, I get a logical address. I get an IP address, most likely. So you could see we have the data link layer here, the network layer, and the upper layers. Let's give an example real quick. One more time, I started with the data. This is my A. Okay? And this is 10. You can see the first thing we did was AP. Why AP? Who's sending to who here? Who's sending to who? AP is the address here. P is whose address? Whose address is P? Look at it. Where was it destined? Where is it destined? You can see here, right? So this is my receiver. This is my sender. The first thing I did is added the A and the P. These are my logical addresses, right? Then I added my physical addresses. So this is the physical address, logical address. Now, the logical address is end-to-end, as you can see. End-to-end. The physical address is for the next, is for the what? The next what? Why did I not put here, for example, 20, or sorry, why did I not put 95, 10? Who could tell me? Because the physical address is hop by hop. The logical address is source to destination, host to host. Okay? So that's the trick here. Obviously, this is looking at the one that's coming after. As you could see, the one after was 20. So when it came here and it left here, you could see what happened to it. Now it became 33, 99. 99 is where it's coming from. 33 is where it's going. Then when it left here, again, you could see 95, 66. It came from 66 going to 95. You see how the physical thing changed from one hop to another, and the logical basically remained the same from the beginning to the end. You could see the AP remained the same from the beginning to the end. So again, the logical is the IP addressing for you to understand for now, and the physical is the MAC addressing. Okay, it remains the same, doesn't change. Is what remains the same that doesn't change is the logical address from the beginning till it comes to the destination. The physical changes from one to another. Okay, you can see now if I added to it process, these are processes. Same thing. You could see the processes AJ, AP. These would basically be from one end to another. AJ, AP will remain from one end to another. What will change from hop to hop? What will change? What will change from one hop to another? What pair will change? The physical. Thank you so much. The physical pair will change. Where is it coming from? Where is it going next? However, you can see the process would remain the same because I need to know who the source and who the destination is process. And the logical address remain the same. That's, again, now you will understand why we need the routing to be host to host, process to process is a transport, and the physical layer is changing from one hop to another. Okay? So when you talk about, as I said, physical addresses will change from one to another. The port addresses is typically represented by one single number. I think I already showed you the port addresses today as well. So you can even see it from the net stat here. If I come and say net stat dash AB, if you say net stat dash AB, you could see, I think I mentioned that before. You can see them. You know, this is where they're actually working. And if you go even to the task manager, you can actually see them as well. Okay? So you could basically know the port number. You can see what ports are blocked. For example, if you go to an organization, they block specific ports. Again, there are famous ports that function at famous applications that work at specific ports, which you can actually block, which would not allow you to access that specific application. So yes, so port is kind of this gateway that allows me to access that specific application. Of course, the internet uses a famous port, the email uses another port, and other applications. So ports are used in association with the processes. So really quick, TCP IP, it was a good standard, it was useful. Again, it was better than OSI for many reasons. Functionality-wise, it was better. There was a whole book that discusses the comparison between OSI and TCP IP. OSI focuses on services, interface, and protocols. It's good for object-oriented programming. TCP IP wasn't very clean in terms of this. So TCP IP was focusing more on the functionality. I want to send the packet, I want to receive a packet. How do I do that? That's why they became very famous about this. What else? The OSI did the model before the protocols. TCP IP did the protocols before the model. They said, let's jump to the protocol, let's people start using it and see how things work. That's why it became very famous. However, it's not very good for new innovation. If somebody wants to implement something new, most likely they will go back to OSI. The network layer in OSI can be either connection or connectionless. In TCP/IP, it's only connection oriented. Transport layer is connection oriented. So this is a kind of a combination between OSI has a network and a transport. So I put them next to each other, it's easier. So OSI is connection and connectionless, the network layer. TCP/IP is only connectionless, which is the IP. OSI, the transport layer, is only connection oriented. The TCP/IP, as I said, the TCP is connection oriented, the UDP is connectionless. So one more time, OSI, the transport layer, it's only connection oriented, which means I establish a connection. Here, it can be both. By the way, this is again TCP and this is UDP. In the network layer of the OSI, it can be both connection and connectionless. However, in TCP, they said, you know what, we only want IP, which is connectionless. So I'm just comparing them together real quick. As I said, this is model before protocol. This is protocol before model. Okay? Again, a hybrid model, usually when we teach, we say, let's talk about the physical data link, which is basically in TCP/IP, these are one layer. And then you have the network, transport, and application layer. Okay? So if you look at telecommunication, we have the ITU. This is kind of a leading organization, which is the International Telecommunication Union. These are the ones who put a lot of the protocols, radio communications, and so on. You also have the ISO, which is the International Standard Organization, also very famous between multiple countries. They came up with most of the standards that we know. IEEE is kind of famous, as I said, IEEE 82.11 and many others. These are all standard organizations that come up with many of the things that you see on a daily basis. You have about the internet, you have something called IRTF, the Internet Research Task Force, the Internet Engineering Task Force, the Internet Society. All these are organizational standards that come up with what we use on a daily basis. So you need to kind of be aware they exist. Because you might come across them. In terms of standards, for example, IEEE, as we know, the IEEE 82.11, this is kind of a leading standard, which is Wi-Fi. This is Wi-Fi. Okay. You have other protocols, of course. You have broadband wireless, which is also referred to as WiMAX. Again, very famous. You have some of them that are almost not very important anymore. Some are very important. For example, Ethernet obviously is the foundation of many things, IEEE 82.3. So you can see these protocols change over time. They have different versions like 82.11. They have A, B, C, D, E, F. You can read about them. They work at different frequencies and so on. Can I re-explain the triple? EEE is an organization, Abdullah. It's an organization, Institute of Electrical and Electronics Engineer, that come up with standards. That's what IEEE is, okay? It's an organization. Yeah. Okay, I think in terms of units, we already kind of saw these units quite a lot before, so let's make sure you're comfortable with them, okay?